For centuries, our understanding of the cosmos was built on a sample size of exactly one. Looking at our own solar system, the blueprint seemed obvious. Small, rocky planets orbit close to the sun, while giant gas planets sit far out in the cold. Everything moved in neat, stable, circular paths. Early scientific thinkers like Isaac Newton suspected that the fixed stars might be centers of similar systems, constructed according to a similar design. But for hundreds of years, that remained a hypothesis. We lacked the proof. The barrier was a matter of physics. A typical star is about 1 billion times brighter than the light reflected by any planet orbiting it. Trying to see an exoplanet is like trying to spot a firefly buzzing next to a searchlight from 1,000 miles away. The glare makes the planet invisible to direct observation. Humanity spent thousands of years assuming the entire universe operated exactly like our solar system. Because we couldn't see past the blinding starlight, we remained unaware of just how unusual our home system really was. In the 1990s, astronomers stopped trying to see planets directly. Instead, they began looking for the subtle behaviors of the stars themselves, searching for hints of hidden companions. The transit method tracks a star's light curve. When a planet crosses in front, the brightness drops slightly, revealing its size. Meanwhile, Doppler spectroscopy measures a star's wobble. An orbiting planet tugs the star, shifting its spectral lines to reveal its mass. These methods eventually confirmed the first planet orbiting a sun-like star. This discovery earned Michel Mayor and Didier Queloz the Nobel Prize in Physics and initiated a new era of astronomical search projects. The first confirmed data was unexpectedly violent. In 1992, the first exoplanets ever detected were found orbiting a millisecond pulsar, the dense, aggressive remnant of a star that exploded as a supernova. While humanity had finally solved the detection problem, the results proved that the universe was far more chaotic than the orderly blueprint of our own solar system. As specialized space telescopes began their work, discoveries flooded in. However, the initial census of the galaxy appeared to favor one specific, bizarre type of world. This was a result of observational bias. Early detection methods were physically predisposed to easily detect only the most massive planets orbiting extremely close to their host stars. This bias led to the discovery of hot Jupiters. These are gas giants comparable in size to Jupiter, but they orbit so closely that a single year lasts only a few days. These planets are subjected to intense stellar radiation. The extreme heat swells the planet's radius and creates violent atmospheric dynamics, as the gas giant is scorched by its host star. The discovery of hot Jupiters completely contradicted existing formation theories. Scientists previously believed that giant planets could only form in the distant, freezing outer reaches of a system where ices could accumulate. These worlds proved that planetary systems are migratory. Planets can drift inward, overturning the logic that seemed to govern our own solar system's history. The Kepler Space Telescope confirmed thousands of new planets, revealing that the galaxy is a bizarre alien zoo. Kepler found eyeball planets, worlds so close to their stars that they are tidally locked. One side is a scorched desert, the other a frozen wasteland. A narrow twilight ring separates them, the only place liquid water might survive. Then there are the evaporators. These are small, rocky worlds caught in such tight orbits that the heat of their parent star is actively destroying them. Low surface gravity allows vaporized metals and volcanic ash to escape into space, creating a glowing tail that follows the planet like a comet.
The census also includes billions of rogue planets. These are gas giants wandering through the pitch-black galaxy, entirely detached from any star system. The diversity of these orbits and environments reveals our solar system to be a highly unusual, exceptionally calm variation. We are the exception to a chaotic rule. Newer satellites like TESS have increased our sensitivity, allowing us to see smaller, cooler, rocky worlds that earlier missions might have missed. This data revealed the Fulton Gap. The galaxy's most common planets seem to come in two specific sizes: super-Earths and mini-Neptunes. There is a distinct lack of planets with sizes falling right in the middle of those two categories. There is a strange irony in this data. These mid-sized worlds are the absolute most common type of planet in the galaxy, yet they are entirely absent from our own solar system. Astronomers had to set aside the blueprint of our own neighborhood before they could calibrate their instruments to find planets that actually resemble home. The ultimate conclusion drawn from the Kepler data concerns the stars most similar to our own. Roughly 1 in 5 Sun-like stars hosts an Earth-sized planet in the habitable zone. This is the region where temperatures allow liquid water to exist on the surface. When you scale that ratio to the 200 billion stars in the Milky Way, the math is staggering. Our galaxy likely contains between 11 and 40 billion potentially habitable, Earth-sized planets. This suggests billions of alien, yet familiar, habitable horizons waiting to be explored. The next frontier is no longer just counting these worlds, but analyzing them. The James Webb Space Telescope is now peering into these alien atmospheres, searching for the specific chemical signs of life. The discovery of exoplanets replaced our local blueprint with a far more complex set of universal laws. We have moved toward the specific search for which of these 40 billion candidates will be the first to answer us.